When your mom told you to drink milk as a kid, you probably thought it was to build strong bones. But the milk might have helped you ace your exams more than pass gym class. That's because calcium is one of the most important molecules in the brain. Calcium not only helps neurons communicate, it also helps translate the messages into things like learning and memory. Recently, researchers at the Max Planck Florida Institute for Neuroscience revealed how calcium signals are transformed into the long-term changes that encode memories in the brain. During learning, synapses, or sites of communication between neurons, turn on in specific patterns. These repetitive patterns of activation result in the long-lasting changes in synapse strength and structure that encode memories. The protein calcium calmodulin-dependent protein kinase 2, or CaMKII, plays a key role in converting synaptic activity patterns into these long-term changes. Normally, CaMKII is inactive because its binding site is blocked, but calcium removes the blockage. Communication through a synapse causes the calcium concentration to spike, turning CaMKII on. But it's been a mystery exactly how calcium spike patterns translate into CaMKII activity. To investigate this question, the researchers optimized existing imaging methods so they could visualize calcium-induced CaMKII activation more precisely. For the first time, they were able to see how CaMKII acts when calcium spikes occur in quick succession. They used laser pulses to activate synapses and evoke calcium spikes in mouse brain slices, and then watched what happened to CaMKII activity. When they applied a fast train of brief pulses, they saw that CaMKII activity spiked in response to each pulse, just like calcium. But the CaMKII spikes lasted longer than the calcium spikes, and added together in a stepwise fashion. Because the signals combined over time, specific patterns of calcium spikes could translate into variable amounts of CaMKII activity, and thus different changes in synapse strength and structure. An important aspect of CaMKII's normal function is that it can also work independently of calcium if it phosphorylates itself at a specific site. This is because the phosphorylation prevents CaMKII's binding site from becoming blocked again. But it wasn't clear whether phosphorylation influenced CaMKII's translation of calcium signals. So the researchers repeated their experiments with a mutant form of CaMKII that couldn't be phosphorylated at this site. The mutant CaMKII activity spikes were shorter than normal. As a result, the activity induced by repeated synapse activation did not add up over time. Long-lasting changes in synapse strength and structure were also impaired. However, stimulating the synapse faster so that the CaMKII spikes could add together restored the functional and structural changes. These results indicate that phosphorylation lengthens the duration of CaMKII activity induced by single calcium spikes, which allows CaMKII to translate patterns of activation into the long-lasting synapse changes that encode memories. Humans have long been fascinated by memory. By revealing how CaMKII reads calcium signals and the importance of CaMKII phosphorylation, this work marks a big step in our understanding of the molecular signals that write memories in the brain.